Let's start with partition trees. Partition theorem is the following theorem. It says given a set of n points in 2 dimensions with a parameter r, which is supposed to be between say 1 and n half or something like that. So this r is an integer. We can partition P into r subsets that are almost equal in size. But this means that they roughly have the same number of points in them, let's say within a factor of 2. And so these subsets are P1 up to PR. So remember that this is a partition, so they don't share any points, and the union of P1 up to PR is the set P. And also on top of that, we enclose the point set Pi into a triangle delta I with the following properties. First of all, the size of the points are almost equal, so that's the size of each Pi is theta of n over r. Pi is inside a triangle, and on top of that, the crossing number of any lines is square root r. I'm going to explain this with a picture. Okay. So for example, if these are my set of points, for example, this could be a particular partition. So I have this orange partition, green partition, I don't know, red, blue, and black partition, right? So these are the subsets. Each subset is inside a triangle. The triangles don't need to be disjoint, but the subset are disjoint, right? So there is no point that is inside the red and the blue subset. But this red triangle may include some of the points of the other subset as well, okay? So I have a R disjoint subset. Each subset is inside a triangle. The triangles they don't need to be disjoint. But what they need to have is this low crossing number property. What this means is that if you draw any line in the plane, for example, these 3 lines, the number of triangles intersected by each line is at most O of R. So for example, this line intersects 3 triangles, so therefore its crossing number is 3. This line intersects 2 triangles, so its crossing number is 2. But the property that we want is that every line in the plane that you can draw, any arbitrary line, must intersect at most square root r of the triangles. And that is also known as the crossing number of the line. Okay. So the partition theorem proves the existence of such a partition, and there's also algorithmic versions of this partition theorem that actually tell you how to build this partition or how to create it algorithmically in good time. We're not going to look at that. We're just going to assume the existence of this partition theorem. If we assume the existence of this partition theorem, then it is relatively straightforward to build a tree data structure. The tree data structure basically works like this. You get your point set, you apply the partition theorem to it. This partition theorem decomposes the point set into R subsets. Then you recurse on each R subset. So now you have R subsets. Each one has roughly n over R points. So n over R in the first one, n over R in the last one. And then you recurse. So this subset will have n over R squared points, more or less, and so on. Okay? So this will give you a tree. In particular, every point will be stored in exactly one leaf. Okay, and let's say you stop once you get to a constant number of points, and then your recursion is stopped and you're at the leaf. This is a proper tree because the subsets are disjoint. So every point is stored in only one subtree. So therefore, this is a tree that has linear space. The height is log because at every recursion we're going down by a factor r. And let's say for the moment r is some constant, so therefore the depth of the tree is essentially just log n. Okay? So that's easy. So we have linear space, logarithmic depth. How do we answer queries? So that part is quite interesting. So let's look at one picture. So let's say we had this partition from the previous picture. So let's say for the moment that our triangle is a special triangle such that it's so big that it's just 1/2 space or 1/2 plane. So let's say that is our giant triangle that includes everything inside this half of the plane. And we want to count the number of points inside this half plane. Okay? If I want to do that, then I look at these subsets. The thing is, I just can look at the triangles, right? I look at this black triangle, I realize this black triangle is completely contained inside my half plane. So therefore, if I just store the number of points inside this triangle, I could just grab that number, and I know that I don't need to recurse anything. I don't need to do anything. I know exactly how many of these black points are inside my query. It's all of them. I just add it to the total that I have. These two partitions are completely outside, so I can ignore them. This orange and blue partitions, they intersect my half plane. So some of the points might be inside, some of them might be outside. So what I can do is recurse into them. Okay, so that essentially is the query. As a pre-processing step, we store the number of points that are contained inside this triangle, or the number of points of that of the subset, and we recurse on the triangles that are intersecting my half plane, or the boundary of my half plane. The triangles that are fully inside or fully outside, I can take care of them easily. Ignore if it's outside, add to the total if it's inside. Okay. So now let's try to, okay, let me go back here. When you look at the picture, the way it works is that you have R children at every node. If the subtree is completely inside, or if the triangle containing the subtree is completely inside, you just grab the number and you don't recurse. If it's outside, you ignore. But if it's intersecting your half plane, then you recurse and you go down to the children of this node. Okay, so that's basically how the query algorithm looks like. It's a very simple algorithm. If we write down the recursion is relatively easy to write down. The number of children that you recurse is O of square root log n, because that's how many triangles you intersect with your line. All the other subtrees you recurse or you ignore. So to process all the other subtrees, you just look at them once. There are R triangles, so you just look at each one in constant time. You get this, and the number of points inside each triangle is theta of n over R, so you get this recursion. Okay, so this is a very easy recursion to write down. To solve it is a little bit tricky, or maybe not too tricky, but in the exercise classes we're going to solve that. This solves to almost a square root n, the square root n plus epsilon, when R is a constant. And if you remember, so that's it. To answer half plane queries, to count the number of points inside the half plane, I just built a data structure that has linear space and has roughly square root n query time. So almost reproducing what I showed you in the previous video.